everyone. I'm going to talk about our work least action dynamics for min-max optimization. This is a joint work with Amartya, Guillaume, and Ioannis, which has been accepted to TMLR. Our paper studies min-max optimization. It's where we would like to optimize with respect to two players, X and Y. These types of formulations appear in different applications in machine learning, such as GANs, out-of-distribution generalization, and also adversarial training. Before starting, I'd like to show you how single objective optimization and min-max optimization are different and what is the problem that we're tackling. So in single objective optimization, we would like to minimize a smooth differentiable loss function f of x, and we usually apply gradient descent. Here I'm also defining the gradient vector field, which is basically points towards the direction of our gradient. And so the update operator of our gradient descent dynamic, we are calling it here the f, and the f basically given a current state of our parameters xt returns the next state of parameters xt plus 1. So the next state of parameters is basically the current applying one step of gradient descent. Now the stable fixed point of this update operator of gradient descent is basically the local minimum. The stable fixed point is basically the point where our parameters do not change if we apply the gradient descent more. It's basically where the gradients are 0. However, in min-max optimization, we would like to optimize with respect to two players x and y. So we're minimizing with respect to x and maximizing with respect to y. Now, what we do here usually is to optimize this game using gradient descent ascent, and the vector field has the following formulation, and we can also write down the update operator of gradient descent ascent. It's very simple, very similar to what we just see for gradient descent. However, the stable fixed point of this update operator is no longer the local minimum, but the local Nash equilibrium. It's where in the state of parameters of both players where they cannot improve their loss locally or unilaterally. Now to study this update operator, to see if it's convergent or not, we do spectral analysis. So f is convergent if the spectral radius or the largest eigenvalue of the Jacobian of f at the fixed point is smaller than 1. So to study the Jacobian of f, we can write it as the following, and we see that the Jacobian of f is dependent on the learning rate and also the Jacobian of the vector field. Now in single objective optimization, the Jacobian of the vector field is basically the Hessian, which is symmetric and has real eigenvalues. And this is well-known dynamics. However, in min-max optimization, the Jacobian of our vector field may not be symmetric. And if you remember from linear algebra, we might have imaginary eigenvalues which correspond to rotational dynamics. And it has been shown that in these types of min-max games, rotational dynamics do exist, and they are in part one of the reasons that, for example, in GANs we have unstable training, the dynamics converge very slowly, and in general they are hard to train. So in this paper, we wanted to study game optimization from a physical perspective. We wanted to gain intuition into these types of games from a physical perspective. And the goal here was to, after modeling the system as a physical system, we wanted to manipulate it such that we can curb these rotational dynamics and have better convergent dynamics. So how does physics and optimization connect? So common intuition in optimization is that polaric momentum, or the heavy ball, is described as an object that's moving inside a potential well, and it's accelerating while moving towards the minimum. So this is an intuition that most of us have, where we can understand polaric momentum from the physical perspective and why we have better rates and we accelerate when we add momentum. But how do we exactly connect it from the physics? So we can start by modeling our system using all the forces that we have in the system. So the net force that is applied on a particle, this is Newton's second law, is equal to the mass of the particle multiplied by acceleration. So this equation gives us a path of the particle in continuous time. We can replace the net force with the gradient. So we just assume that the particle is inside this potential well, and the gradient is basically applied to the particle. Now, given this continuous time equation of motion, we can discretize it and we get the Polyak momentum optimization algorithm. So this is very interesting, and what we wanted to do was to have the same understanding for game optimization. So we basically followed the same recipe. We started by modeling min-max optimization as a physical system, and the important point here was that we wanted to see the rotational dynamics in this physical system as well. And then we introduced relevant forces in the system to curb or reduce these rotations. Then we will write down the equation of motion using Newton's second law, and this will give us a continuous time equation of motion using all the forces in the system. Given the continuous time equation of motion, we discretize it, and then we have the optimization algorithm. So this is basically the recipe that we followed in the paper. So the step one was to model min-max optimization as a physical system. So the continuous time dynamics of gradient descent ascent with momentum in a 2D plane is the following formulation. This is what I just showed you, but in continuous time. And we realize that this dynamic is similar to a force in nature, which is called the vortex force. And if we apply the vortex force on a particle in a 2D plane, what you're seeing down here, we observe that the particle slowly moves away and it increases the velocity as it moves away. So the vortex force had two important aspects. It exhibited rotational dynamics and it increased the velocity. These points were also what we were observing in min-max games. So now that we're in the physical world, we know different forces, we know their interactions, and we can just add different types of forces to our system. So we introduce another force to curb the rotation. What we designed was we assumed that the particle is inside a magnetic field, and a magnetic force is also applied to it. So now, if you look at this plot here in 2D plane, we see that the magnetic force does change the rotation of the particle. It does change the direction. However, we don't see convergence to the equilibrium because it is known that the magnetic force only changes the direction of the movement and not the velocity. So since we were increasing the velocity using the vortex force, we were not observing convergence. So what we needed now was to introduce another force to reduce the velocity. And so what we did was we added dissipation in the system, and the simplest form was friction. So we added friction to the system, and we observed that the particle basically converged easily to the equilibrium. So the two aspects of the vortex force, rotational dynamics and the increase of velocity, were both handled by the magnetic force and the friction. And we basically observed convergence. So we basically have all the forces in our system. We have our particle, and applying Newton's second law, we basically have the equation of motion in continuous time. So we want to go back to the optimization world, so we just have to discretize the system. And once you discretize it, you get this optimization scheme, which we call it lead, or the least action dynamics. And lead has several terms, the current state of parameters, the momentum, and the gradient. And we also have this new term, and this term basically corresponds to, for each player, for example, for X, while taking the next step, it looks at how much the other player has moved in the previous steps, and also it looks at the lost landscape or the curvature. And actually we showed that we have lots of theory and also lots of experiments in the paper. But the most important one was that lead outperforms big GAN in terms of FID with an architecture that is almost 30 times smaller than big GAN. And we had very interesting results in the paper and lots of analysis in comparison with different types of methods.